realized at the end of the problem that I had done the start wrong.
And Catalina, we're getting ready to take notes.
So does she go by Cat? No, does she go by Cat?
Yeah, get your notebook out. We're
She
taking
saw
notes.
it. Shout out Catalina. It's on video. Shout out Jerry.
Jerry Farmer.
Is that your guys' hair? Jerry? You guys remember Jerry?
Yes. Oh my gosh. The magic school bus.
Oh my gosh. Do you remember that?
Who's Jerry?
Remember that I got some random kid watching my videos?
Yeah,
that.
Jerry. Shout out Jerry if you're still watching my videos. Shout out. You know? We've come so far. But anyway, Catalina saw my mistake. Didn't say anything at the very beginning. I could have corrected myself. It's all her fault. It is all. That's weird. It is also her fault that my U key is gone on my keyboard. She said, "Well, it was sticky, so I brought it down to not like really sticky, but like when I pushed down on the right side, it wouldn't click, but on the left side, so I was like, can you just like try to pop that up and maybe like fix it?" Well, she popped it up and broke it. So now I don't have a U key.
You still know it's you though. Does it still work? Right.
Well, the problem is it's in my password for everything. So like, I keep getting like,
Good to know.
you got one more try and then it's gonna expire. Yeah, figure out. Yeah, like you could figure that out. Like, okay, it contains the letter U. You guys are way getting me off track. Okay. Actually, this is me getting myself off track. Exponential functions. So we were here yesterday talking about the applications of exponential functions. Guys, the only thing I really want to say about the applications of exponentials is that the applications are like, they happen all the time, and they especially happen within nature. Okay, we've got exponential growth and exponential decay happening all around us all the time. I just want to highlight a couple of the book examples that they give you. I think we talked through the population one yesterday, but this is the population over the course of 1900 to 2010, and the population exponentially increasing. There is slight variance off that. They actually make special note of that, and they say, where did the population dip below the expected value? They were like, oh, look, the population dipped below the expected value right here. And they give a little history lesson because what happened here? The Great Depression, World Wars, things like that. And then the baby boom happened and things kind of took off after that. But you get the idea there. This is another example of exponential decay. In 1995, a paper appeared detailing the effect of the protease inhibitor, ABT, whatever, this drug on HIV. Table 2 shows the value of the plasma viral load, basically meaning how much virus is still in the blood, or in the plasma, I guess you could say, of a specific patient. Okay, so what's happening here? We're seeing an exponential decline in the viral load, right? So that's a good sign, right? But we see an exponential decay. Is it completely gone? No, it looks like it's still going to level off a little bit, but at least it's maybe going undetectable. But let's get into half-life. We studied half-life with an E in it. When we did in Algebra 2, we did the formula e to the negative kt, where k was like the decay constant. I would like to show you in terms of an exponential decay function without e. We'll talk about e in a second. But this process is really going to help us kind of understand, wrap our brains around what an exponential function is going to do and how to create it. Okay, the half-life of this substance is 25 years. This means that half of any given quantity will disintegrate in 25 years. And remember what half-life is, it's constantly decaying. It's not like in 25 years, as soon as the clock turns over on 25 years, half of this thing is going to disintegrate. No, it's over the course of 25 years. At that point, that's when half of that substance should remain left over. So A says, if a sample has 24 milligrams, find an expression for the mass. Now, to kind of figure out what this expression is going to be, let's take some values. First one being, what is m of 0? At time 0, how many milligrams of this thing do I have? At time 0, when I start. 24, right? 24. At time, now let's pick a convenient amount. At time 25, how many milligrams of this thing do I have? 12. At time 50, 6. At time 75, 3. And this process could keep going, right? It's going to keep getting lower and lower and lower and lower and lower. Will it ever reach 0? No, and again, that's the idea of having an asymptote. It's going to keep taking half of it and half of it and half of it and half of it, but it's never going to make it completely go away. Okay, now we have all of these coordinates. Maybe we can create some sort of function. Maybe we can analyze it and see what's happening here. Well, how did we find m of 25? We found m of 25 by taking 1/2 of 24, right? Well, how did we find m of 50? We took 1/2 of 12, right? Well, isn't 1/2 of 12 a half of 24? And I could keep that process going. Well, how did we find the 3? Well, it was 1/2 of 6. And isn't 6 this expression? Half of 24. 1, 2, 3. And that can keep going. You know, this was 1/2 of, so I've got 2, 3, 4. Now, that looks really messy, like that. So let's try to simplify that down a little bit. Okay, well, this is 1/2 squared times 24, right? 1/2 times 1/2. I don't want to make that 1/4 because you'll see why here in a second. But that's 1/2 squared. That is 1/2 to the 3rd. This is 1/2 to the 4th times 24. So in this case, that could still be written 1/2 to the 1st times 24. Well, what about our 0? Right, 1/2 to the 0 times 24, because it would be 1/1 times 24. So maybe there's some way where we could figure out the equation by using this. Well, okay, if I've got a power in the denominator, what's another way I could represent the power in the denominator? What do powers in the denominator actually mean in terms of the exponent? It's a negative exponent, right? So this is like 2 to the negative 1 times 24. This is 2 to the negative 2 times 24. This is 2 to the negative 3 times 24. This is 2 to the negative 4 times 24. So how do we actually run those numbers? Well, those are the amount of half-life cycles that I've gone, right? 24 is a consistent product there, right? I'm multiplying by 24 the entire time. So if I want to generalize this to m of t, I know that this is going to be this standard 24. And I'm going to put it out front just because, I don't know, that's what we usually do with exponentials. We always put our starting value out front, a times b to the x. But we've got to find our base raised to. Our base is 2, that's standard. 2 to the negative what power? Well, I know I want these half-life cycles. So what I'm going to do here is take the time. Like say I plugged in 75. How many half-life cycles was that? That was 3 half-life cycles, right? So how do I get it to be 3? Well, I take the time that I'm plugging in and I divide it by 25 because that's how many half-life cycles it'll do. So t, that's a t, over 25. And that's our equation. That's our equation here. And that'll let me do any year, right? I made these coordinates conveniently with half-lives, but now I can find any year, which is what part B asks me to do. Part B says after 40 years. See, okay, I can kind of guesstimate it a little bit. I know it's going to be somewhere in between 12 and 6. closer to 6 than it is to 12, so maybe like 8, something like that. So let's find it. That would be m of 40. So that would be 24 times 2 to the negative 40 over 25. Let's evaluate it. 24 times 2 to the, and I'm going to put it in parentheses, negative 40 over 25. 7.9. 7.9. I was pretty close. It actually says to the nearest milligram, so I'll say 8 milligrams. 7.9 or 8 milligrams. Okay, let's take a look at example C here. Using a graphing device, graph m of t, and use the graph to estimate the time required for the mass to be reduced to 5 milligrams. So let's go into our graphing calculator and plug this in. Looks like I've got 24 times 2 to the, let me put this in parentheses, negative x divided by 25. I didn't need this first parentheses. It was going to do the exponent first anyway, but whatever. Overkill. Now, when I want to find, I'm just going to plug this in right now. When I want to find when it's going to get down to 5 milligrams, isn't that a y value? 5 milligrams? Isn't that an output? The input is the time, the output is the milligrams. So that means I want to know, I'm going to need to do this, right? I want to know the x value when it's going to get down to 5. So I'm going to zoom 6 because, again, we've been doing some funky stuff in our calculators. Now, why don't I see anything on the screen? Well, oh, whoops, I guess. Why don't I see the exponential on the screen? I thought all exponentials had a y-intercept of 1. Wait a sec. That was before we put any number in front. That was before we did any sort of vertical stretch out. What is the y-intercept in this case? What is my starting value? 24. So that's when the y-intercept may change, when you put a number out front and you're multiplying. All right. I'm going to zoom. Now, there's a couple different ways around this. You could zoom fit it. You could just manually change your window. Whatever you want to do, you want to see the intersection point on the screen. So I like to do zoom fit. Zoom 0 is zoom fit for me. And we'll let it run and see what it looks like. I have to see the intersection points on my screen, though. I don't. So I know it's going to converge somewhere out here. We could, let's manually change our window. I can kind of estimate the x value that it's going to be, right? It's going to go down to 5 milligrams, right? Somewhere in between 50 and 75, right? I know at 75, it's already gone down to 3, right? So let's just go into our x max and say 75. Because that's going to put me here. That's what I mean, manually change your window. I guess I should have also done, I want to go below my 5 value here. Let's just go to 0. There it is. So you want to manually work with your window until you see the intersection. Second, calculate. Choice 5 is intersect. First curve, enter. Second curve, enter. Guess, enter. There it is. 56.57. Let me move down here. 56.57. This is part C. So it's going to get down to 5 milligrams in 56.57 or 58 years. 56.58 years. Which makes sense. I mean, it's somewhere between 50 and 75. And I know it's probably closer to 50 than it is to 75. So 56.58, yeah. You can estimate it like that, but use the equation to figure out the answer. Did we have to do anything else there? Use the graph test. Nope, that was it. Questions about that? Okay. Now we want to talk about E. E. You know how yesterday I had said that the most common exponential function was 2 to the x? That's going to change today. Now the most common one that we're going to use is e to the x. Because e to the x is actually a really convenient base to choose when working in calculus. And you'll see why here. Of all possible bases for an exponential function, there's one that's going to be most convenient for our purposes in calculus. The choice of a base b is influenced by the way the graph crosses the y-axis. The wording is especially important there. It's chosen because the way e to the x is going to cross through the y-axis. Not where it crosses through the y-axis, but the way, the angle at which it crosses through the y-axis. Because they're all, I mean, as long as it's not vertically stretched or shifted, they're all going to cross through it at 0, 1, right? So like 2 to the x, 3 to the x, and e to the x are all going to be crossing through at 0, 1. The difference is the way they cross through. Take a look at the diagram for 2 to the x and 3 to the x. Look at the slope that we have for how it crosses through 0, 1 at the instantaneous tangent line at 0, 1. Look at the slope of that line. It's 0.7. Okay, look at the slope of 3 to the x at 0, 1. Whenever you talk about a tangent line, you've got to talk about a tangent line at a given point. You know, if I chose a tangent line at 1, 3, well, then that would be a lot steeper line, right? Then the slope would change. But look at what I have here. At 2 to the x, it's 0.7, and 3 to the x, it's 1.1. Now, I don't know if you guys remember what e actually calculates to be, but it's 2.71828 and so on, right? What do you think the slope is going to be if I look at e to the x? Exactly 1. Let me show you here. There's, and they put all 3. I wish they would have just done e to the x, but that's okay. E to the x is the middle one. The one in, is that purple? The purple one in the middle there, right? Sorry, I'm red-green colorblind, so I can't really tell the difference between colors sometimes. Is it? Okay. So this is 2 to the x. The blue is 2 to the x. The green is 3 to the x. And the middle is e to the x. If I were to go in and find the slope of the tangent line at 0, 1 for my middle line there, it would be exactly at 1. Guys, we're going to be working with the slope of the tangent line, the instantaneous slope, like the whole year. Like that's calculus, really. Finding instantaneous rate of change, instantaneous velocity, instantaneous slope. Okay, the instantaneous slope at 0, 1 actually ends up being 1 for e to the x, and that's why it's going to be really convenient for us. Okay, but again, e is our exponential number. As with like everything in mathematics, this guy Leonard Euler coined the letter e. I always thought that it was for his name, because his first, that's how you pronounce it, Euler. But that's I always thought it was e because I don't know his last name. But he says it's because it's the exponential constant. The exponential constant. This number kept coming up over and over and over again. And I think, you know, if you had, for honors algebra 2, I remember when we introduced E, we did that whole discovery where we, doubled $1 every year, then every half a year, then every month, then every day, then every minute, then every second. And it kept leveling off to a certain number. And that number was actually E, the exponential constant. But just remember that E is just a number. Like, I'm going to graph this, and like I could have just graphed the exact same way, 1/2 2 to the negative x minus 1. But we're going to just look at 1/2 e to the negative x minus 1. I guess the first thing is to think about what the parent looks like, e to the x. E to the x. Okay, so this is, I'll put it in black here, e to the x. Crossing through it, 1, 0, 1, with a slope of 1 at that point. So there is e to the x, just the parent e to the x. Okay, what are my transformations on e to the x? I see three things going on. Can anybody tell me what those three things are? What's one of those things?
Down one.
Down one. Right. I see a down one with the minus one. What else? What's the 1/2 doing? What's the 1/2?
Vertical compression.
Vertical compression by a factor of 1/2. Yeah. Why is it not horizontal? Because it's not up in the exponent. Horizontal things happening on the inside, right? So it's a vertical compression. And what's the negative doing up in the exponent? The other one, the y-axis. It's reflecting across the y-axis because I'm changing the x value. Now, in what order am I going to apply these transformations? Well, think about order of operations. If I plugged in a number for x, what would act on it first? The negative, right? The negative would act on it first. So that's what we're going to apply first. We're going to reflect over the y-axis. And then I would take e to that whatever power and then multiply by 1/2 to it. Then I would shift it down 1 unit. Okay, and here's where I made my mistake earlier. Guess what I did? I stupidly reflected across the x-axis, and nobody said anything as I was doing it.
Stupid.
Okay, let's reflect over the y-axis now. Now, is my y-intercept going to change when I reflect over the y-axis? No, it should not change. All it's going to do is going to change it from exponential growth into exponential decay. So that is my first transformation. Vertical compression by a factor of 1/2. Vertical compression by a factor of 1/2. So it's just going to kind of make it shallower, right? It's going to make it shallower. It's going to take that y-intercept and go from 0, 1 to 0, 1/2. And then I'm going to shift it 1 unit down. So since this was at 1/2, this is just going to go to negative 1/2. That's my y-intercept now. I'll put this in purple here. Oh, yikes. Well, okay, I got to do that. That looks bad. Because I want to keep it the same steepness as the green, because all I'm doing is shifting it downward. Okay, that's pretty good. And that's my final. Now, you have your calculators. Let's plug it into our calculator just to confirm. I didn't notice it was wrong until this moment. Okay, so we've got, let's do just the plain old e to the x. Remember, e in your calculators is underneath the division symbol, e to the x. And we've got 0.5 e to the negative x minus 1. Zoom 6. There's my original. There's my new. Okay, so yeah, what we're seeing here is the black and then the purple. I think we did a pretty good job. We have to finish this off by stating the domain and range. What's the domain of any exponential? All real numbers. Doesn't matter what I plug in. You might be tempted to say that there might be an asymptote on the left side. There's not. There's not. It's going to keep going on forever. Now, where is our range? I guess a better question might be, where is my asymptote? -1. -1. Why is it at -1? Well, think about each transformation. The original was the axis, right? That's e to the x. Okay, did the reflection change that? No. Did the vertical compression change that? No. Did the shift 1 down change that? Yes. That's when it got, yeah. that's when it got shifted 1 unit down. So that's why the asymptote is at y equals -1. So that means my range is going to be -1 and above. -1 and above. -1 to infinity. Not negative infinity to negative. -1 to infinity. All right, we're not going to do that last example. We're just going to end right here. Okay. And bell rings at 32. You got 18 minutes. I'm going to close the recording.